Hello and welcome to the next lecture on this course on pattern recognition. We have been discussing the support vector method. We have looked at the basic support vector machine algorithm. So, this class we will just briefly review the support vector machine method and then move on to study the kernel methods, the kernel functions, which we only briefly touched upon. We did not look at any kernels. So, this class will look at kernels in more detail. So, to recap, we have been discussing the support vector machine. Basically, it amounts to formulation of a optimal separating hyperplane problem. So, we have seen how to define an optimal separating hyperplane and generate an optimization problem whose solution is the optimal separating hyperplane. And we have seen that this problem is solved more easily in the dual form and by using a kernel function we can implicitly map the feature vectors to a higher dimensional space and then find an optimal hyperplane there. This has been the overview of support vector machine so far. So, I will quickly recap this before going forward. So, the optimal hyperplane is a solution of the following constraint optimization problem. The optimization variables are W and B. Recall that our notation is that our feature vectors are in m dimensional space. So, W is also in Rm, B in R. So, you want to minimize half of W transpose W subject to yi into W transpose xi plus b greater than or equal to 1. Xi, yi are the examples, there are n examples, and for a given WB, if W transpose xi plus b into yi is greater than 1, which means if yi is plus 1, W transpose xi plus b is greater than 1, y is minus 1, W transpose xi plus b less than minus 1. So, these are the separability constraints. Separability, so that if I want to take W transpose x plus b equal to 0 as my optimal hyperplane, then on the margin is given by the space between W transpose x plus b is equal to 1 and W transpose x plus b is equal to minus 1. So, if for all I is equal to 1 to n, if these constraints are satisfied, then this particular WB represents such a separating hyperplane, and for that hyperplane this is the inverse of the margin. So, by minimizing this we maximize the margin and we minimize this over only those WB which represent separating hyperplanes. Okay. So, that is how optimal separating optimal hyperplane is a solution of this problem, where you are saying find a separating hyperplane, that are my constraints, such that the it has the maximum margin, okay, because margin is inverse of this. To maximize margin we are minimizing this. This is a very nice optimization problem. You have got a quadratic cost function, linear constraints. It is almost a delight for any optimization theory algorithms guy to solve such a problem. Coon-Tucker conditions are necessary and sufficient, every local minimum is a global minimum. So, it is a very nice and simple optimization problem to solve, and we showed that we can find the dual of this problem. If this is the primal problem, so we can find the dual of this problem. Dual will be on the Lagrange multipliers. There are n inequality constraints, there will be n Lagrange multipliers, call them mu 1, mu 2, mu n. Then the dual maximizes this function of mu, right. We derived the dual last class subject to these constraints. Okay. I will not go into the derivation, but this we derived last class. So, and the primal dual relationship tells me that if this has a solution, so has the dual, and the optimal values are equal. And more importantly for us, from the Coon-Tucker conditions, for example, W star is given in terms of the optimal Lagrange multipliers. So, if I know all the Lagrange multipliers, I know immediately the W and B, right. That is the final solution. Final solution W star is mu I star y I x I and B star is y j minus x j transpose W star for some j such that mu j star, this should have been, I am sorry, mu j star is greater than 0. This comes from your equating the gradient of your Lagrangian to 0, and this comes from the complementary slackness condition as you derived last time. So, if I solve this dual, I can obtain the mu I stars, and once I get the mu I stars, I got my final solution W star and B star. Note that the dual is also a quadratic cost function, linear constraints. The dimensionality of the dual is n, which is equal to the number of examples irrespective of the dimension of xi, and the input vectors xi themselves come only as inner products here. Okay. Now, unfortunately, this problem has no solution if training data are not linearly separable. This is the primal we started with. If there is not even one WB that satisfies these constraints, then there is no feasible solution and hence no optimal solution. So, the problem has no solution if training data are not linearly separable. Then, like in any standard optimization problem, we use slack variables. So, the problem becomes y into W transpose xi plus b greater than or equal to 1 is what we wanted. If we can't get it greater than or equal to 1 minus j I. Now, given any W on B, for every xi yi in my example set, I can find a j I such that this is satisfied. So, every WB is feasible now, right. There is no problem about any feasible solution, but now I cannot just minimize W transpose W, because if I am not satisfying this constraint fully, right, j I is my slack variable. So, this much slack is there in satisfying this constraint. So, I want to satisfy it with as least violation as possible. So, I also add sum of j I. We are assuming j I greater than or equal to 0, or not assuming, constraint j I greater than or equal to 0. So, each constraint, if I can correctly satisfy it, if there is a separating hyperplane, then possibly j I could be 0. If j I are 0, then it will be like whole solution. But even if I do not have a separating hyperplane, then I would like to satisfy these constraints as much as possible. So, I use slack variable j I and add the summation j I to the cost function. So, I minimize of W transpose W also plus some constant times summation is equal to 1 to n j I. This tells me the total violation of my constraints. C is a user specified constant. As we discussed last time, essentially this optimized problem will always have a solution. If I take C larger and larger, it essentially means that I am preferring only separable hyperplanes. We will not tolerate even little bit of violation of constraint. If C is small, I am allowing violation of constraint to improve margin. Okay. Unfortunately, there is no simple way to say how C affects this. We will discuss this a little while later, but right now we will simply say that remember that C is a user defined constant, and using the slack variables allows us to ensure that even if the data is not linearly separable, this optimization problem will always have a solution. Okay. So, this is the optimization problem we want to solve, and very nicely the way we formulated it, the niceness about the formulation is that its dual is very similar to the old dual. The cost function does not change, this constraint does not change, only change is that earlier I had only 0 less than or equal to mu I, I have 0 less than or equal to mu I less than or equal to C. Essentially, my primal has C here, if C, as C tends to infinity, this becomes same as the whole problem. So, in the dual, that is the only thing that comes, which is very convenient for me. If I want to solve the primal, now I have increased the number of optimization variables, all my data come in the constraints. But if I am solving the dual, putting C or not putting C is simply a matter of, while solving this problem, whether or not I have an upper bound on mu I, right. That is the only difference. So, when I am solving the dual, I can just throw in a C, solve it. If I want, I can increase the C constraint and resolve it to see how my mu I change. That tells me whether I am finding a good separating hyperplane or not, and so on. So, when I am solving in the dual domain, whether I put that extra constraint or not is simply a matter of putting one extra upper bound on all my Lagrange multipliers. The solution is still the same. Once I solve this, W star is mu I star y I xi, B star is yj minus xj transpose W star for some j. Now, the complementary slackness means that this is for some j such that mu j is strictly between both 0 and C. Okay. Earlier we are only saying mu j is strictly greater than 0. Okay. Now, given this, then we moved on to ask how can I use this method to solve nonlinear classifiers, to obtain nonlinear classifiers. The idea is that the basic SVM idea is that we map the feature vectors into high dimensional space and then find a linear classifier there. What that mean? Originally I am in the m dimensional space. So, I may use a transformation phi that maps Rm to Rm prime. Phi, even though is non-bold here, it is a vector valued function. Okay, remember that. So, in the Rm prime space, the new space, what will be the training set? The training set will be Zi yi, where Zi is equal to phi of xi. Earlier the training set is xi yi, that is in the m dimensional space. Now, in the m prime dimensional space, the training set will be Z I Y I, where Z I is phi of x I. Now, with respect to Z I want to find a linear classifier. That is same as we can find optimal hyperplane by solving the dual. What does that mean? My dual is this. The only way access come is here, right. So, these are the feature vectors. So, if I am finding a linear classifier in the Z domain, this simply x I transpose x j becomes Z I transpose Z j. So, we can solve the dual by replacing x I transpose x j, Z I transpose Z j. That means that this is the dual I will solve. So, it is very simple. Basically, if I calculate all the Z I is equal to phi x i's from my given training set, I just have to replace x I transpose x j by Z I transpose Z j. Once I solve this, I can find my optimal W in R m prime. W star is mu I star y I Z I, B star is this. The nice thing is that my original feature vector is m dimensional space, maybe 100 dimensional space. My transform feature vector may be in 10,000 dimensional space, but the dimensionality of the dual does not change. The dual is an optimal R n, where n is the number of examples. It does not depend on what the dimension of x is or what the dimension of z is. So, that is a very nice thing, another advantage of solving in the dual domain, and we can solve this and find this. The only problem of course is to do this. I have the examples for each x I have to calculate z I, that may be a costly calculation, right. Then of course, I do not have to do it in, I can only once compute z I transpose z j, even that is costly computation, and then I solve this dual. Then I have to calculate W star, which is in the high dimensional space, and from now on every time you give me a new vector x, I have to find z is equal to phi x, and then I have to do z transpose W star. So, there is a lot of computation to be done, even though I can automatically find a optimal hyperplane in the high dimensional space by solving the dual, but even this can be avoided. This is what we said last time. Suppose there is a function k that takes two m dimensional vectors and gives me a real number. So, that k x I x j is phi x I transpose phi x j, there is z I transpose z j. We call say a function kernel function. What do you mean by there is such a function? Of course, there is such a function. If you give me phi, I can define k x I x j to be phi x I transpose phi x j. What we mean is that phi might be very expensive function, phi x I might be 10,000 dimensional vector, whereas x I is only 100 dimensional vector. In that sense, phi x I transpose phi x j might be 100 times more expensive than x I transpose x j, because x I transpose x j involves only 100 multiplications, phi x I transpose phi x j may involve 10,000 multiplications. By saying that there exists a kernel function, we mean that this function is such that computation of k x I x j is roughly about as expensive as computation of x I transpose x j. If I have such a function, then I can replace z I transpose z j by k x I x j and can solve, which means in my dual I do not have to actually calculate all the z i's. This z I transpose z j is replaced by k x I comma x j. K x I comma x j is about as costly to compute as x I transpose x j. So, it is like I am just finding a linear classifier in the original space, because I replace x I transpose x j, what was there in the original linear classifier, by k x I x j, which is about roughly same computation. So, at least for solving the dual, the kernel function is useful. Now, what happens after I solve the dual? After I solve the dual, I have obtained W star. So, even though in the dual I can replace z I transpose z j by k x I x j, ultimately W star lives in the m prime dimensional space. So, does it mean that I have to always take every vector into the m prime dimensional space and then use W star to classify it? No. As it turns out, the kernel also helps me to find the classification of any new pattern also very efficiently. Let us say mu I star is the solution of the dual, then we know W star is mu I star y I phi x I, right, because it is a linear classifier of the z domain. So, it is mu I star y I z I, which is same as mu I star y I phi x I. Now, first let us see how I can get B star. I know B star is y j minus z j transpose W star for a appropriate j. Now, z j is phi x j. Now, phi x j transpose W star can be written as W star transpose phi x j. W star is this. So, it will be yj minus mu I yi phi xi transpose phi xj. Now, phi xi transpose phi xj is k xi xj. So, you do not have to actually calculate any phi xi's or phi xj's for calculating B star. I can do it only in terms of k xi xj. Now, is that good enough? Yes. What do I have to do? Given a new pattern x, I effectively need to compute z transpose w star, that is phi x transpose w star plus B star. Given an x, I have to first transform into the z, that is phi x, then there I use the optimal hyperplane. So, I have to calculate phi x transpose w star plus B star. Now, w star is given by this. So, this term is w star transpose phi x. So, this transpose phi x. So, that is mu I yi phi xi transpose phi x plus B star. Now, phi xi transpose phi x is k xi x, B star is this also can be written as k xi xj. So, everything can be written in terms of the kernel function now. So, if I solve the dual and store all my mu I stars and the corresponding xi's, then given any new pattern, I have to just calculate this to decide its classification. I calculate this and based on its sign, I will say class plus 1 or class minus 1, and to calculate this, I never need to calculate any phi x's, right? Because we already agreed that k xi x is about as complicated as xi transpose x, and more importantly, I never need calculate phi xi or phi x if you give me the kernel function. So, this is really an interesting way of learning a nonlinear classifier. We solve the dual whose dimension is that of n number of examples irrespective of what is the high dimensional space in which you are finding the classifier. All we need to store after we solve the dual are the non-zero Lagrange multipliers and the corresponding training data xi, which are called the support vectors. Once I have that, I know how to calculate classification of any new pattern. This is all I need to calculate the classification of any new pattern, right, which means I never need to enter the phi x space at all. I never need to calculate phi x for anything. I do not even know where, in some sense, if you tell me the k, the kernel function, I do not even need to know what phi is. I do not even need to know what the range space of phi x is, right. So, this is what support vector machine is. What does support vector machine do? I essentially obtain mu I star by solving the dual with z transpose zj replaced by k x x. All it means is I choose a suitable kernel function. Now, I can use a penalty constant c if needed, I can choose a c, and as we said, using a penalty constant c is simply a matter of putting an upper bound on mu. So, in the dual solution, it is a very simple thing to incorporate. Once I got my mu I stars, I store non-zero mu I and the corresponding support vectors. Now, I am ready. Give me any new pattern, this is what I compute and classify. So, if you have a suitable kernel function, we never need to compute phi x, we never need to know what phi x is. As a matter of fact, in a manner of saying, the range space of phi can even be infinite dimensional for all I care, because I never need to compute a single phi x, right, as long as I have a kernel function. So, now let us ask, where do kernel functions come from? So, let us start with a simple example in 2-dimensional feature vectors. Let us say we are working in R2. So, take a kernel function k xi xj is 1 plus xi transpose xj whole square. As a point out, this is about as expensive as translating xi transpose. Suppose xi is here of course is 2 dimensions, but in addition to xi transpose xj, once I calculate xi transpose xj, all I have is one addition and one multiplication to get the square, right. So, it's just one multiplication more than xi transpose xj. We will use the same kernel function any dimensions later on as we will see. So, if xi is a 100 dimensional space, xi transpose xj involves 100 multiplications, whereas k xi xj involves 101 multiplication. So, k xi xj is about as expensive as xi transpose xj. So, if I represent the two components of xi, I am looking at 2-dimensional vectors here by xi1 and xi2, and similarly xj as xj1 and xj2, then k xi xj is 1 plus xi1 xj1 xi2 xj2 whole square. This is nothing but xi transpose xj, okay, because the 2-dimensional thing. This is what my kernel function is. We are now going to show that there exists a map phi, okay, so that k xi xj is phi xi transpose phi xj, and we are also going to show that this map is such that a linear classifier in the phi x domain is actually a quadratic classifier in the x domain. So, as earlier let us choose phi R2 to R6 given by 1 root 2 into x1, root 2 into x2, x1 square, x2 square, root 2 into x1, x2. This R2 to R6 is very easy to see that a linear discriminant function in terms of z. So, a linear function in terms of z will have terms a constant, terms of x1, terms of x2, terms of x1 square, x2 square and x1, x2. So, a linear classifier, a linear discriminant function in terms of z would be a quadratic discriminant function in terms of x. Well, that is the whole idea of SVM. Now, we are going to show that with this transformation k xi xj, that is 1 plus xi transpose xj whole square is actually phi xi transpose phi xj, which means if I use this kernel function, I am effectively finding a quadratic discriminant function, right, using just a linear technique, right, because if I wanted a linear thing, you would have been xi transpose xj. I want a quadratic thing is simply 1 plus xi transpose xj whole square, right. I am still solving the same dual. Okay. So, let us show this first. So, what will be phi xi transpose phi xj? Now, phi xi will be or zi will be, it will be xi1, xi2, xi1 square, xi2 square, xi1, xi2. Similarly, for j. So, when I take phi xi transpose phi xj, I will get 1 here, root 2 will give me 2 xi1 xj1, 2 xi2 xj2, right, 2 xi1 xj1, 2 xi2 xj2. Similarly, I get xi1 square, xj1 square, xi2 square, xj2 square, and once again this root 2 will give me xi1 xi2 into xj1 xj2 with a 2 in front. This is what zi transpose zj is. Now, I can easily see that this is same as xi1 xj1 xi2 xj2 whole square. I get 1 xi1 square xj1 square, xi2 square xj2 square and then 2 xi1 xj1, 2 xi2 xj2, 2 xi1 xi2 xj1 xj2, right. So, k xi xj zi transpose zj, phi xi transpose phi xj. So, easy to see it works for and in general, right. The only reason we took 2 as you can see now is because it becomes cumbersome to write this expression, right. If I have x1 x2 xn, x1 square x2 square xn square and all pairs, then accordingly get all of that and accordingly get this square, right. So, this works in general for Rn, which means if I use this results in learning a quadratic discriminant function. So, in the dual, if I wanted to learn a linear discriminant function, I would have used xi transpose xj. Instead that I use 1 plus xi transpose xj whole square, which is a one time computation dual, and then I can use the same function in my final classification. I get a quadratic discriminant function. Right. The other thing that we want to mention is that for a given kernel function, neither the mapping phi nor its range space is unique, right. So, we chosen this particular phi, but for the same kernel function many other phis work. What other phis work? Very easy to see what other phis work. For the same kernel function, instead of taking the last component as root 2 into x1 x2, suppose I have taken it to be not R2 to R6, but R2 to R7 and the last two components are z are x1 x2, x1 x2. As you can see, if I do z transpose zj, I get xi1 xi2 into xj1 xj2 plus xi1 xi2 into xj1 xj2 and you add them, I get 2 xi1 xi2 xj1 xj2. That is what earlier the root 2 x1 x2 term was giving me. So, basically very trivially I can exhibit another phi, another dimension for the range space and which works with the same kernel function. So, for a given kernel function, the mapping phi is not necessarily unique, there can be many mappings. Okay. Okay. So, how do we in general obtain kernel functions? We know the kernel function has to be symmetric because k xi comma xj is phi xi transpose phi xj, the inner product that is transpose is symmetric. So, it has to be symmetric. So, what kind of symmetric functions can be will be represented as inner products in some appropriate space? We currently define two characterizations for this. Okay, one of them we may expand later on, but right now let us define two ways of saying when a function will satisfy what we want. First is called what is called Mercer's theorem. The kernel functions that satisfy this are called Mercer kernels. Mercer theorem says that given a symmetric function which maps Rm cross Rm to R, there exists a space H. I call it an inner product space, meaning in the space H there is an inner product defined. Inner product is like your dot product X transpose Y. Okay. So, there exists a space H. Technically this is called a Hilbert space, meaning is a vector space in which there is a norm of vector defined, inner product between two vectors defined, and with respect to this norm the space is closed, meaning every Cauchy sequence is convergent there. If you do not understand what I am saying, it does not really matter, that is not at present important. So, basically given any symmetric function, there exists a space H in which an inner product is defined and a mapping phi Rm to H, so that k x1 x2 is phi x1 transpose phi x2 for all x1 x2. This is what we want. Such a thing is true if the k satisfies the following: for all square integrable functions g, k x1 x2 g x1 g x2 dx1 dx2, this integral should be positive. By this integral, this actually because x1 x2 are m dimensional vectors, this is a integral over R to m, or if you want, it is a double integral over Rm, right, Rm cross Rm. So, because there is a dx1, that is one integral over Rm, dx2 there is another integral over Rm. G is a square integral function, meaning g square x dx, integral g square x dx is less than infinity. So, given any such g, k should satisfy this. If k satisfies this, then such a k will be a kernel function, because there will be an appropriate phi satisfying k x1 x2 phi x1. So, any kernel that satisfies this theorem is called a Mercer kernel. We do not prove the theorem, but I will show you how to use this theorem to show that the previous kernel that we considered is really a kernel function. A second characterization of kernels is what I call positive definite kernels. So, given a kernel function and some data x1 to xn, let us make a matrix, an n by n matrix k bar, whose ijth element k bar ij is k of xi xj. This will be a symmetric matrix, because this kernel function is symmetric. Then we say the kernel function is positive definite if the matrix k bar is positive semi definite for every n and all data sets. What does matrix being positive semi definite mean? The quadratic form of the matrix should be greater than or equal to 0. So, we can actually write it. What it means is, given any positive integer n and any n feature vectors x1 to xn from Rm, and then given any n and any x1 to xn, then for every set of n scalars c1 to cn, n real numbers, summation over ij ci cj k xi xj, this is the quadratic form of the matrix, is always greater than or equal to 0. So, a function, a symmetric function k is said to be a positive definite kernel if for every positive integer n and any feature vector as x1 to xn in Rm, given this, we have summation over ij ci cj k xi xi greater than or equal to 0 for every set of n scalars. Okay. Now, as it turns out, if the space you are working in is compact, for example, Rm is compact, any real Euclidean space under the standard Euclidean norm is compact. So, if the space in which you are working is compact, then a Mercer kernel and a positive definite kernel are the same, one and the same. Okay. These are somewhat subtle concepts which do not concern us in this particular course, but we can just remember this. So, these are the two ways in which I can form kernels. Okay. Now, let us use the Mercer's theorem to show that the function we gave earlier is a kernel, okay, and we use that proof to motivate a few more kernels. But we do not start with that function, we start with slightly different function. Let us say I have a function k of u comma v, any two vectors u v is u transpose v to the power p. Earlier we used 1 plus u transpose v to some integer, namely square there, But in general, let us say we start with u transpose v to the power p. U transpose v is nothing but I is equal to 1 to m ui vi whole to the power p. So, a function this is symmetric k u v u transpose v to the power p, where p is a positive integer and u and v are vectors in R m with these components. Okay. Consider this function. We are first going to show that this is a kernel function. To show that, let us first look at this expression. This is u1 v1 plus u2 v2 plus um vm to the power p. So, I can use a multinomial expansion. If I use a multinomial expansion, what are the kind of terms I will get? I get a sum of products. Each product is u1 v1 to the power r1 into u2 v2 to the power r2 into u3 v3 to the power r3, so on, right, where r1 r2 are such that we form their sum should be p. For example, the binomial case, I will get 0 on p, 1 on p minus 1, right. So, you get u1 v1 to the power 0, u2 v2 to the power p, u1 v1 to the power 1, u2 v2 to the power p minus 1, u1 v1 to the power 2, u2 v2 to the power p minus 2, and so on. But in a multinomial case, there will be ui vi to the power ri, where ri satisfy r1 plus r2 plus rm is equal to p, and the coefficients turn out to be this kind of combinatorial coefficients. The summation is over all non-negative integers r1 to rm that satisfy this. Okay. So, any something like sum of m terms raised to the power p can be expanded as sum of products like this using a multinomial expansion. So, keeping that in mind, what is it we have to show? We have to show that k x y k u v g u g v d u d v is greater than or equal to 0. I am sorry, not greater than 0, greater than or equal to 0. Now, because this du dv I actually written it as two integrals just to make it clear to you. Du and dv both are in represent integrals for Rm, and this is my kuv. Now, if I use the previous expansion, this thing to the power p can be written as sum of this, because the finite sum, the inside integral is a finite sum. So, I can pull the sum outside. So, by expanding it, this becomes a sum of integrals, right. What will each integral be? Each integral will contain one of these terms into gu, gv, du, dv, right, because this is sum of this. If the sum is pulled out, each integral will be this, which means using that it becomes a sum of integrals, where each one, each integral will have a term that p factorial by r1 factorial r2 rm factorial, u1 v1 to the power r1, u2 v to the power r2, um v to the power rm, gu, gv, du, dv. Now, you see what do I have here? u1 to the power r1, u2 to the power r2, um to the power rm, gu can come out of the v integral. What is the left is v1 to the power r1, v2 to the power r2, vm to the power r. They are the same integral, because u and v are of course dummy variables of integration. So, this is nothing but u1 to the power r1, u to the power r2, um to the power of rm, gu du whole square, and hence is always greater than or equal to 0. So, this shows that this function u transpose v to the power p is a kernel, is a Mercer kernel for every positive integer p. Starting from here, now we can show that now suppose I have another function k u v is not just u transpose v to the power some one power, but some a j times u transpose v to the power j, where j's are integers going from j is equal to 0 to p. So, it is a0 plus a1 u transpose v plus a2 u transpose v square, a3 u transpose v cube, and so on all the way up to ap u transpose v to the power p, where all the coefficients are non-negative. This is also a kernel. Why? This is what I have to show. This is k u v, this summation j is equal to 0 to p a j u transpose v power j g u g v d u. This is what I have to show to be positive. Now, this sum can come out of the integral, right. Now, this integral I know is positive, because I already shown that u transpose v to the power j is a kernel. So, this is because aj's are positive, this is true, right. So, what this means is that functions of the form k x1 comma x2, which is given as j is equal to 0 to p a j x1 transpose x to the power j, are kernels. What is the special case? 1 plus x1 transpose x2 power p. If I expand this in Brown theorem, I will get 1 plus some constant into x1 transpose x2 plus some other constant into x1 transpose x2 square and so on. So, in general this kind of functions are kernels and hence this is a kernel. So, this is the kernel that we used earlier. Okay. This is called a polynomial kernel. It is called a polynomial kernel because we know, as you see, if we put p is equal to 2, this kernel effectively finds a quadratic discriminant function in the original space. So, in general if I put p, it is giving me a discriminant function which is polynomial of degree p. Now, let us say instead of looking at a finite sums like this, suppose I have infinite sums like this, a j u transpose v to the power j. Once a j's are still positive, but now infinite sums. Where will be the problem? Earlier, when we tried to show that this thing, the sum will be inside the integral and I pulled out the sum out of the integral. Now, this can always be done for finite sums, but if it is infinite, then the question is, can I pull the summation, can I interchange the summation and the integral? I can do so if the summation is uniformly convergent, right. So, if I consider the infinite sums, a proof only involved interchanging integration and summation, finite sums is always possible. For infinite sums, a sufficient condition is that the above sum is uniformly convergent. So, if a series like this which are uniformly convergent, then they also form kernel functions. Now, using this we can find another interesting kernel now. Let us say I consider a function e to the power k of x1 comma x2 is e to the power of x1 minus x2 transpose x1 minus x2 by some constant, we call it 2 sigma square because it looks like a Gaussian. Essentially, e to the power of minus norm of x1 minus x2 whole square by 2 sigma square. This is a kernel because e to the power of x1 minus x2 transpose x1 minus x2. If I expand this, I get an e power minus x1 transpose x1 term, e to the power minus x2 transpose x2 term, and I get e to the power 2 x1 transpose x2 term. And you already seen what you have to do in the Metzger theorem. We got k x1 x2, gx1 gx2, dx1 dx2. So, if k x1 x2 can be perfectly factorized into a term involving only x1, a term involving only x2, then I am done, because one goes with gx1, other goes with gx2. Ultimately, I want to show that to be a square of an integral, right. So, essentially e power minus x1 transpose x1, e power minus x2 transpose x2 pose no problem. Only this cross term we have to know what to do, but the cross term can be written as an infinite sum like that in the Taylor series expansion. Now, because in the exponential, this is the Taylor series of an exponential function, this is uniformly convergent and hence using what we shown earlier, this becomes a kernel, right. So, let us put all this together to look at the kernels. So, these are some of the very popular kernels one uses with SVMs. One is called the polynomial kernel Kp. Kp of x1 x2 is defined to be 1 plus x1 transpose x2 to the power p. As you have seen, this is essentially gives you a polynomial of degree up to p, degree p. This is called the Gaussian kernel, what you have just considered, x1 minus x2 e to the power minus norm x1 minus x2 whole square by some constant, normally written as sigma square or 2 sigma square. Essentially, this can give rise to an effective phi whose range space is infinite dimensional, because as we ultimately saw, it involves this x1 transpose x2 to the power p kind of terms, where p goes all the way up to infinity. Another interesting kernel is what is called a sigmoidal kernel. Ks x1 x2 is tan hyperbolic a x1 transpose x2 plus theta. Of course, instead of tan hyperbolic, I can also use sigmoid, that is, I can write this as 1 by 1 plus e power minus a x1 transpose x2 plus theta. Okay. I just put tan hyperbolic for because we are considering ultimately functions that go both positive and negative. These are some of the popular kernels used. These two already shown to be kernel. This I haven't, but similarly it can be shown to be a kernel function. Let us just take a look at what some of the kernels mean. Suppose we use the Gaussian kernel. If I use the Gaussian kernel, what will be my final classification new pattern after learning? Fx is mu I star yi k xi x plus b star, that is what I will calculate, right, as we already seen. Now, k xi x is nothing but e to the power minus xi minus x whole square by 2 sigma square. this is what I calculate. What does this look like? You think of mu I star y I as some constant, v star as some other constant, then this looks exactly like what? A Gaussian RBF network, right? So, if I have a standard Gaussian RBF network, x is the input, then the output of the hidden node, output of the ith hidden node will be e to the power minus norm of x minus the center of the ith hidden node whole square, and then you multiply the output of the ith hidden node with the weight from the hidden node to the output node, and this is the bias of the output node. So, this is exactly a RBF network, Gaussian RBF network, and the centers of the hidden nodes are the support vectors. As you seen, when we did RBF network, we said we actually want some relevant, very important vectors to become the centers. So, here the support vectors become the centers. Okay. As we have already mentioned, the support vectors are a very important byproduct of the SVM. See, the support vectors are the one closest to the separating boundary, and as seen, those are the only vectors at which the inequality constants satisfied by equality constants, which means the solution of the optimization problem is not going to change if I leave the support vectors in and take away all the other training data. If I remove all the training data, leave only the support vectors, now ask you to find the optimal hyperplane, you would still find the same one. Right. So, in that sense, support vectors are essentially the most important from the point of view of classification, because they are closest to this classification boundary. If I know how to separate them, I would separate the rest of the patterns anyway. So, in some sense, support vectors are the most important of your examples as far as the classification problem is concerned. Okay. So, in that sense, support vectors are a very important byproduct. We will see some examples next class. But here, as you can see, if I use a Gaussian kernel, an SVM with a Gaussian kernel is equivalent to the Gaussian RBF neural network, where I do not have to worry about how to find the centers and so on. Right. As a matter of fact, there have been many people use algorithms whereby you solve an SVM, you get these support vectors, use them as centers of your RBF, but may not use these Lagrange multipliers, you relearn the output weights using a linear regression. Okay. But any case, this expression shows that SVM with a Gaussian kernel is equivalent to a Gaussian RBF neural network. Similarly, SVM with a sigmoid kernel is equivalent to the other neural network, right. Classification of x is determined by this. So, substitute the function k. So, what is this? Xi I can think of as the vector of weights mapping the input layer to the ith hidden node in the hidden layer, where there is only one hidden node. So, then the net input into that hidden node, the ith hidden node will be A x transpose xi, if A xi is the vector of all the weights that are coming into the ith hidden node. Theta could be the, theta is the bias of the ith hidden node, and this is the activation function of the ith hidden node. Then these are the weights from the ith hidden node to the output node, and this is the bias of the output node. So, this is same as the output of 3-layer feed-forward network with one output node, and tan hyperbolic activation function for all the hidden nodes, whereas linear activation function for the output node. Essentially, there are as many hidden nodes as their support vectors, and weights into the hidden node are given by the support vector. So, once again support vectors, see in our sigmoidal neural network, one thing that we did not know how to choose is the number of hidden nodes. Right. So, once again, if I use a support vector machine with a sigmoidal kernel, what I get is essentially like a 3-layer feed-forward network with sigmoidal activation functions, and where the support vectors determine the hidden nodes. Okay. So, in that sense, these kernel functions are very nice. SVM with kernel functions gives rise to nonlinear classifiers that we have already seen earlier. Okay. Now, let us go back to the beginning. We said that the basic idea of SVM is learn a linear classifier in a transformed space. You know. So, the idea is from the original feature space, you transform all the feature vectors into high dimensional space and there land a linear classifier. And we also said that the naively doing this will not work, right. To just transform it and do a linear classifier landing there will not work. What are the two problems? We said this is curse of dimensionality, there are two issues. If I naively transform, if I want a quadratic classifier, as I said, if I have 100 dimensional feature vector to start with, it becomes 10,000 dimensional feature vector. If I want a cubic classifier, 100 dimensional feature vector becomes a million dimensional feature vector. So, naively transforming will get us caught in the so called curse of dimensionality, and in this curse of dimensionality there are two issues. One is computational complexity. One is I said we have to first transform all of them into very high dimensional space, do inner products in the high dimensional space to learn the classifier. Even after learning the classifier, you give me any new pattern, I would now once again transform it to high dimensional space and keep doing inner products in the high dimensional space. So, computationally very complex. This is elegantly solved by the kernel tree. By using the kernel function and solving the optimization problem in the dual, by choosing a optimal hyperplane, solving the optimization problem in the domain and using the kernel, we never need to actually compute the transformation. We never need to compute the inner products in the high dimensional space. So, the computational complexity issue is elegantly solved by the kernel trick. There is the second issue in the curse of dimensionality, does it generalize well? For all my cleverness, I am still learning a hyperplane classifier in 10,000 dimensional space. So, it should have a VC dimension of 10,000 and hence how can I get around, how can I land with anything less than 10,000 into 10 times 10 into 10,000 examples, so to say. Well, so the idea is, because you are finding a hyperplane in a very high dimensional space, do we need correspondingly larger number of examples to get good generalization? As it turns out, in practice, SVMs perform very well. That is, they learn classifiers that do very well on test data without needing get correspondingly large number of examples. You need as many examples as you would have needed if you are learning a linear classifier in the original domain. Why does this happen? The reason essentially is that we learn a hyperplane with a large margin. We are not searching for any hyperplane classifier, but hyperplane with a large margin. Different ways to analyze. For example, we can ask VC dimension of hyperplane classifiers is dimension plus 1, but suppose we restrict ourselves to all classifiers with a minimum margin of delta, right? Then the VC dimension will change, obviously, right? Which then it will not be same as the set of classifiers, set of just hyperplane classifiers, right? So, we can, for example, ask what will be VC dimension of large margin classifiers. There is a way of looking at it. Currently, we are not looking at this. What I will do is, we will just get one theoretical result in this lecture. Much later, I may come back to this. Okay. The result is the following. Let us say PNE error be the error rate on test set for an SVM trained with n random examples, meaning for a given n, I choose n random examples, train an SVM and now use this SVM to find error on a test set. The probability of error on a test set is given by this, right. Obviously, this is a random variable, because it depends on n random examples. If I use different n random examples, I may get a different SVM and hence it will have a different test error rate. But if I ask what is the expected error rate when I land with n random examples, one can bound it above by a minimum of these three numbers. What three numbers? S by n, where S is the number of support vectors. So, S by n is the fraction of support vectors. Out of n examples, how many happen to be support vectors? Or R squared norm W squared by n, where R is the radius of the smallest sphere enclosing all the examples, and 1 by norm W square is the margin of the maximum margin hyperplane, right. So, essentially this keeps decreasing as you increasing the margin. Third is the usual thing, your dimension by the number of examples. So far, we only know this from our VC theory, because for linear classifiers, VC dimension is essentially proportional to the dimension of the feature space. So, this is the dimension of the feature space and is the total number of examples, right. This is for SVM with no slack variables, you learning a linear classifier in a m-dimensional space. Okay. Now, let us try and make sense of this. This is what we have. Expected error rate is minimum of these 3. So, we can essentially say that optimal hyperplane, as I said, everything is happening because we are learning optimal hyperplane. Optimal hyperplane may generalize well because of many reasons. One is that the data compression is large. What does that mean? S is the number of support vectors, n is the total number of examples I have. If S by n is small, then I know expected error rate is small. So, if only 1% of my data turn out to be support vectors, then I have a good chance that I have got a very good classifier, because expected error rate is bounded above by 0.01. Right? So, essentially we see the support vectors are the most important subset of my training examples. If you keep the support vectors and throw away everything else, I will still get the same optimal hyperplane. So, in some sense support vectors represent the rest of the examples as far as the classification problem is concerned. So, if I got a very good insight into the classification problem, that is what data compression means. I can compress all the examples to a few support vectors. That may be the key to my good performance. As a matter of fact, this is very nice, because when I use a support vector machine, at the end I have some way of guessing how good would be the classifier I learned, not using a test set, simply by looking at the fraction of support vectors. If I got 20% of my data support vectors, I do not know, I may have got a good classifier, may not have got a good classifier, because of course, this is only an upper bound. But if I finally landed up with only 1% of my examples being support vectors, then I have a very good confidence that I have learned a good classifier. So, one reason optimal hyperplane may generalize well, because we are not learning any hyperplane, we are learning optimal hyperplane, that is when the support vectors come into play, is because data compression is large. The 2 is, of course, if margin is large, that also will help. Right? So, if I have one large margin, that also can result in error rate being small. Third is the usual thing that we know. If I got many more examples than the dimension in which I am learning the linear classifier, then also is small. So, what it means is, even if m is very large, let us say m is 100 times n, right. I have got actually less number of examples than I have 1000 examples in a million dimensional space. M is 1000 times n, but if one of these two terms is small, then also I can learn a good a low error classifier. This is basically what learning the optimal hyperplane is buying us. I want to emphasize again that this is for a learning a linear SVM in m dimensional space without the slack variables. This is when you actually learn an optimal subtraining hyperplane. Once we put slack variables, we can't actually use the theorem, but roughly if C is sufficiently large, if I think that I am getting a subtraining hyperplane, the theorem would kind of hand waving would be useful. But for a subtraining hyperplane, even if m is large, meaning if I replace m by m prime, keeping n same, m prime by n might be much larger than 1, but s by n can still be small, or the margin can still be large, so that my expected error would be much smaller, even though I do not have sufficient number of examples. Right. This is basically how learning optimal hyperplane is helping me. Okay. So, both in terms of computational cost and in terms of generalization abilities, posing the problem as one of learning optimal hyperplane, solving it in the dual and kernelizing the inner product, gave us a very, very elegant solution. Okay. So, let us sum up the kernel trick. We use a function phi to map the original space into some high dimensional space. Kernel function allows us to compute inner products in H implicitly without using or even knowing the transformation phi. Through kernel functions, we learn nonlinear classifiers using linear techniques. We can elegantly construct nonlinear versions of many linear techniques, right. Essentially, between learning a linear classifier and a nonlinear classifier, I simply solve the same dual problem, where xi transpose xj is simply replaced by k xi transpose xj. So, using a kernel, I can take a linear technique and convert into a nonlinear technique, right. We can use this trick in many other algorithms. Right. We can similarly design Fisher linear discriminant wherever the actual training data enter into a solution only as inner products, only in terms of Xi transpose Xj. By canalizing Xi transpose Xj, we can take a linear function, a linear technique and turn it to nonlinear technique. For example, I can use kernels and turn Fisher linear discriminant into a non-linear Fisher discriminant. Okay. So, let us look at the same thing in the regression context, okay, for the just to see how the kernel trick can be used. So, what is the regression problem? Unlike classification problem, I am given data xi, yi. So, x1, y1, x2, y2, xl, yl. We want to find the best function to predict y given x, right. Xi's are in m-dimensional space. I put L here, sometimes we will use L as the number of examples, sometimes we will use N as the number of examples. So, in general, we search in a parameter class of functions. So, we are learning a function gxw, which is written as w1 phi 1 x plus w2 phi 2 x, wm prime phi m prime x plus p, right, which I write as w transpose capital phi x plus p, where each phi I is a Rm2 R function. So, this is what the kind of linear least squares method we see in where phi's are pre-chosen functions. But then of course, I have to solve this m prime dimensional problem, right. Now, basically the two ways of looking at it. Of course, if you choose phi x equal to xi, then it is a linear model, m prime is equal to m and phi I x is equal to xi, the ith component, then it is simply your w transpose x plus p, your linear model. Otherwise, as we said, it is like choosing some fixed functions, but what we are going to think of it as, actually I think of z is capital phi of x. So, transforming m dimensional x to m prime dimensional z, and then we are essentially learning a linear model in the transform space. This is the basic idea of SVM, right. So, the question is, can we use the kernels? See, we could have done it using linear least squares, but if you want to do it using linear least squares, then I have to actually solve the m prime dimensional space, m prime dimensional optimization problem, and every time you give me an x, I have to actually calculate phi of x, then do w transpose phi x plus b to do my prediction. So, the idea is that can I do it using kernel trick? As it turns out, we can do this using kernel trick. Okay. I just give you a basic idea of how we are going to do this. Like in all regression problems, we essentially minimize a loss function, right. This is the strategy of empirical discrimination. We choose some loss function. So, given a particular xi, I am saying g xi comma w for a given, if w is my model, I am saying g xi comma w, where I should have said yi. So, L yi comma g xi comma w is the loss, sum over all I, that gives me the empirical loss, and that is what I minimize. So, essentially what we are going to show is that we will have a special loss function, using which by doing empirical disk minimization, we can use kernel trick while learning linear regression. This is what we will see in the next class. Thank you.